In this video we're going to look at a table of logical equivalences. I've just split the table into two here just to fit it on the screen. Now we're going to start by looking at what are called the identity laws. P and T is equivalent to P. We can write that in a different notation. This AND operator is written as a dot, as we've seen in earlier videos. The other identity law is that P or F, where F is false of course, is equivalent to P. The other notation for that, for the OR operator, is plus. So P plus 0 means false, is equivalent to P. Here I have a truth table for the first identity law. Proposition P has two values, 0 or 1. T, which we can also denote by 1, just has the value 1. So we want to look at these two combinations, 0 with 1 and 1 with 1. For this column we have P and T, which we can write as P dot T or P dot 1 if we like. So we have the two ways to show these. Now P and T is true only when both P and T are 1s. So when P is 1 and T is 1, then P and T is a 1. Otherwise it's 0. You can see that this column here is equivalent to this column here. So P is logically equivalent to P and T. So this double arrow means logically equivalent. So P and T is equivalent to P. It's not the biconditional operator. You saw in previous videos that the biconditional operator looks like this. This means if and only if. It looks similar, but it's not. This just means equivalent to. Now let's look at the second identity law. Here are the two values for proposition P, and F means false or 0, so it has value 0. So we want to look at these two combinations. So let's look at P or F, which we can write as P plus F, and we can write 0 for F if we like. P or F is only true if at least one of these is true. At least one of P or F is 1. In the first row here they're both 0, so it's false. In the second row one of them is a 1, so it's true. So again you can see that this column, the P column, and the P or F column are identical, which shows that P is equivalent to P or F. Let's look at the first domination law. P or T is equivalent to T. The other notation for this of course is P plus 1 is equivalent to 1. So here's a column for P, here's a column for T. T is 1, all 1s of course. P or T is true when either P is 1 or T is 1. So both of these are 1s. You can see that P or T, this column is identical to the T column. So these two columns are identical. So that shows that P or T is equivalent to T. That's that bit proved. Now let's look at the second domination law. P and F is equivalent to F. Well, F column just consists of zeros. P and F, we want to get this 0 and 0 here. Well, that gives us 0. And when P is 1 and F is 0, we get 0. P and F is only true when both P and F are both 1s. So that's not the case here. So you can see that this column here and this column here are the same, showing that P and F is equivalent to F. Let's look at the first idempotent law. P or P is equivalent to P. So we need a column for P. P has values 0 or 1. We want to combine P with itself. So we need a second column for P. But of course when P is 0, we have to combine 0 with 0. We can't have 0 here and a 1 here, because that would mean that P has two values at the same time. P is both 0 and 1. That's impossible of course. So when P is 0, so when this value is 0, this value is 0. 0, 0 in this row, and we have 1, 1 in this row. So we just have 2 rows in this table, not 4 rows as we would have if the two propositions are different. Now let's look at P or P. P or P is false when these two values are zeros or false. So one of them has to be true for P or P to be true. You can see now that the column for PRP is identical to the column for P. So that proves that PRP is equivalent to P. If we look at P and P is true when both these values are ones. It's false otherwise. So we can see that this column is equivalent to P. So that proves the second idempotent law. The double negation law is very easy to see. If we have P, then not P, when P is 0 is 1, and when P is 1 is 0. Not P is got by flipping these, so when not P is 1, not P is 0, not P is 0, not P is 1. So you can see now that this column is the same as this column, showing that not P is equivalent to P. Another way to write the not operator is this symbol here. The commutative laws are very straightforward. PRQ is equivalent to QRP. When we're talking just about arithmetic, you might have heard of the commutative law for addition, which states that 2 plus 3 equals 3 plus 2. It's also true for multiplication. 2 times 3 equals 3 times 2. So for the OR operator and for the AND operator, the commutative laws hold. Let's look at the first associative law. The associative law is similar for the operation OR. It's similar to the arithmetic operator plus. Like 2 plus 3 plus 4. For adding three numbers, we can take any two numbers. So at a time, suppose we're adding 2 plus 3 plus 4. We can also, instead of adding 2 plus 3 first, we could add 3 plus 4 first. So the addition operator in arithmetic is associative. And the same is true for the logical operator OR. To prove this associative law, we need to look at the three propositions P, Q, and R. So this column has the values that R can take on, which is 0 or 1, alternating in steps of 1, 0, 1, 0, 1, 0, 1, 0, 1. Then if we say take Q, we go in steps of 2, 2 zeros, 2 ones, 2 zeros, 2 ones. And finally for P, we go in steps of 4, 4 zeros and 4 ones. So we have 8 combinations altogether. It's 2 by 2 by 2 is 8. Now, let's look at PRQ. PRQ is true when either P is true or Q is true. So you can see it's false here. It's both the first two rows, P's and Q's are both 0, but in the remaining rows, at least one of the values of P or Q is a 1. So we have all 1s down here. Now, let's look at P or Q or R. So we take this column and combine it with this column R, and we get a 0 if both values are 0 as they are in the first row, and we get a 1 for the rest of them because 1 appears at least once in the remaining rows. Now let's look at Q or R. That's the bit in the brackets here. So Q or R is 1 if one of these is 1. It's 0 otherwise. It's 0 in the first row. It's 1s in the next 3 rows. This row here in the 5th row, both Q and R is 0, so Q or R is 0, and in the remaining rows we have 1s. And finally we can look at P or Q or R. So we look at the column for P and the column for Q or R, and if we have 2 zeros appearing, then this has value 0. So in the first row we have a 0 here for P and a 0 here, so we get 0 here, and we get 1s for the remaining rows because 1s appear at least once in the remaining rows. 0 here, 1 here. The third column we have a 0 and a 1. Fourth column we have a 0 and a 1 here, and so on. In the fifth column we have a 1 and a 0. Notice that this column is the same as this column. These are logically equivalent. So that proves the associative law for the OR operator. Similarly, you can prove it's true for the AND operator, which I won't bother doing. The first distributive law, this one here, was proven in an earlier video, so I won't prove it again. It gives the distribution of the OR operator over the AND operator. So P, R, Q, and R is equivalent to PRQ and PRR. So we can distribute the P into the brackets here. Similarly, we can actually swap the OR and the AND operators around. So we can get P and QRR, and we can distribute the P into the two brackets. So we get P and Q or P and R. I won't bother proving this. The first of De Morgan's laws says that not P and Q is equivalent to not P or not Q. So that's what I'm proving here. So I have a column for Q and a column for P. Column for P and Q. P and Q is only true when both P and Q are true. Not P and Q is got by flipping the values in this column. So the zeros becomes 1, 1 becomes 0, of course. Here's a column for not P. Just flip the values in the P column. Here's the P column. Flip these two zeros to two ones. These two ones become two zeros. Here's the not Q column. We flip the values in the Q column. And then we want to look at not P or not Q, which we can write as P bar plus Q bar. So not P or not Q is true when at least one of not P and not Q are true. So in the first three rows here, ones up here, so we have ones here. In the fourth row we have two zeros, so not P or not Q is false. So now we can see straight away that this column here is equivalent to this column here. So not P or Q is equivalent to not P or not Q. So we've proven the first of De Morgan's laws. Now the second De Morgan law is got by replacing the dot with the plus. So we get not P or Q is equivalent to not P and not Q. I won't bother proving that. The first complement law, P or not P is equivalent to true. So here is P, its value 0 or 1. Not P is got by flipping these values. What about P or not P? Well, P or not P is 1 when either P or not P, at least one of P or not P is 1. Similarly here. What about P and not P? Well, P and not P is only true when both P and not P are true. See, we just have ones in this column, so we can label this column T for true, and we have just zeros in this column, so we can label it F for false. So we can see that P plus not P is equivalent to T, and P or not P is equivalent to T, and P and not P is equivalent to F. We can write 1 for T or 0 for F. The first part of material implication says that P implies Q is equivalent to not P or Q. So here we have P and Q. We have columns for P bar and Q bar. Let's look at P implies Q. So if P is 0, then P implies Q is vacuously true. So here P is 0 in this second row. The third row, P is 1, Q is 0. So P is true, Q is false. So P implies Q is false. That's the exception. The fourth row, P is true, Q is true. So P implies Q is true. Let's look at P bar or Q. So P bar, not P or Q, is true if at least one of these is true. So in the first two rows, we see that that's the case. The third row, they're both false. So P bar or Q is false. In the fourth row, we have 1. Let's look at Q bar implies P bar. So if Q bar is 1 and P bar is 1, then Q bar implies P bar is true. If Q bar is 0, it's false, then Q bar implies P bar is vacuously true. Here we have Q bar is true, P bar is false, so this is the exception. So this is the 1, 0, 0 exception that we saw earlier. Q bar is false here in the fourth row, so Q bar implies P bar is vacuously true. Now we're after showing that this column is identical to this column here. So the first part of material implication is true. So P implies Q is equivalent to not P or Q. The second part says that P bar plus Q is equivalent to Q bar. Well, P bar plus Q is this column here. I'm sorry, the second part is that P bar plus Q is equivalent to Q bar implies P bar. So here's the column for Q bar implies P bar, and we can see that this column is indeed equivalent to this column here. Finally, the third part of material implication says that Q bar implies P bar is equivalent to P bar implies Q bar. So we need a column for P bar implies Q bar. So P bar implies Q bar. So P bar is true, Q bar is true. So the implication is true. P bar is true, Q bar is false. So the implication is false here. And the last two are vacuously true. Actually, there is a misprint in this final part of material implication. Not Q implies not P is equivalent to P implies Q. So we just want P implies Q here. And using the other symbols, we just want to get rid of this not symbol. So now I have a column for P implies Q. So P implies Q is true when P is false. So the first two rows P is false. So the first two rows here are true. And third row we've 1, 0, 0 situation. P true, Q false. So P implies Q is false. In the fourth row we've both P and Q are true. So P implies Q is true. So now we can see that this column is equivalent to this column. These four columns are equivalent. The first absorption law says that P and P or Q is equivalent to P. Let's look at P or Q. It's false when both P and Q are false, otherwise it's 1. We want P and P or Q, so we're going to combine this column with this column. It's false when both P and P or Q are false. It's only true when they're both true. So it's true for these last two rows, and it's false here because we have a 0 here for P and a 1 here. So we have both of these have to be 1s for it to be true. So we can see that this column is equivalent to P. This column is equivalent to this column here. Now let's look at P or P and Q, which we can also write as P plus P dot Q. So we're looking at the P column, and we want a column for P and Q, which I haven't actually shown. So I'll do that now. So P and Q is only true when both P and Q are true. So that's for the fourth row. It's false otherwise. So now we want P, this column, or this column. So it's false when they're both zeros, first two rows, otherwise it's true. So you can see here that this column P is equivalent to this column here, which proves the second absorption law. The second absorption law can be got from the first absorption law by replacing the AND symbol with OR, and the OR symbol in here with the AND symbol.